Robin, I see that you're on here. I don't know if you heard I was telling Adam that your question made me go check out the the beam deflection activity. Does it make sense what I do and what I think they're asking you to do? Okay. I don't know if Robin, lights go. I don't know if Robin is here or not. Sorry.
On the list, but not in.
Yeah. Okay. Well, I'll approach her again when we get going.
Well, other than that, were there any other questions? Everybody's just pretty good to go?
Had some pacing questions, and I forget who asked me that, but the question is, where should they be? And I think some of that depends on when they test. I test the third week in May, which I know is a lot earlier than a lot of folks that go through school through June, but we are out before Labor Day. So we are starting 2-3. My kids have milled their dog bones. Their samples are ready to go. So we will start talking. We tested on 2-1-2-2 today. We're doing that on Thursday. So on Friday we'll start 2-3. So if you and I'll get through all of the content. So if you kind of gauge where you are in that. And then you can kind of look at my calendar on my website to see where that is. But I really think being in 2-1, even if you're testing in May, if this is your first year, is not bad. Because Unit 1 is really long. Unit 2, especially the statics part, can take a while just because there's a lot to learn. But I find that you just keep going and you just continue to give them trusses and let them have time to kind of marinate in it, but keep moving and then come back to it. So every one of my tests will have some sort of trust question on it, and that way we come back and revisit it all the time. Adam, do you have thoughts on pacing?
Yeah, sounds pretty good. I'm actually starting 1-1 right now. So I'm back with the semesters. I start back all over again. So I'll be going back to the curriculum. Sometimes fun because you get to see what you did wrong the first time and try to improve upon it the second time. Refresh your memory, if you will.
Right.
But yeah, if you're figuring like you're halfway through the year in the curriculum, if you're in the middle of Unit 2, that's pretty good to go. Especially like Unit 4 is not too long, relatively short. So.
Right. And I think your first year, they don't expect you to get through all the curriculum, and so I think you need to understand that in your scores. You need to cut yourself some slack on those scores. So I think that they acknowledge that there's a little bit of a learning curve on that. I understand that everybody kind of wants to get to all of it, but sometimes that's not possible.
All right. Any questions out there before we start getting into new content? All right. Hopefully pretty good. So what we're going to do today is kind of wrap up Unit 2. The problem that we have in Unit 2 is actually not a super difficult problem, but it is one that I do use. Typically, it can be done in a day or two type of thing, so we'll go over that. Then we're going to get into kind of the basic beginning stuff in Unit 3. Parents will kind of show us the test bed and go through that setup, if you will. So let me share my screen. So the way that you're probably finding out now is each unit set up with a bunch of introductory lessons, and then the culminating lesson is supposed to be this design problem. And hopefully the content that they learn in these first couple of lessons should get them into this design problem where they're reapplying all these different concepts before if you decide to give them some unit test. Um, Unit 2 is set up similar to that. The design problem is not super complex. It's using basically this program called West Point Bridge Designer, which is a fun program. The students really like to play around with it. But there's really not like a super in-depth problem where they have to do any calculations or anything to that effect. It's just kind of go through the software, go through the steps, and they kind of play around. So this is actually an activity a lot of times I'll use if I know I'm going to be out, because they can very easily walk themselves through it without your guidance. Maybe show them up one day, like the day before, and then let them go. So if you take a look at 2.4.1, structural design, what it has them do is, walks them through how to use this program called West Point Bridge Designer, which is freeware. A lot of people have already used this. A lot of my students have already used it before they get to my classroom. It talks about the different setup at the beginning. What's nice about this program is they get to reapply concepts. So when they're looking at member properties, they can look at the size of the beam, the cross-sectional area. They can reapply that whole calculation for centroids. They can look at some of the terminology they're using again, where we get into stress and strain. They talk about modulus elasticity. We look at the difference between a hollow beam versus a solid beam. So there really is some depth of knowledge that they're bringing back up, but there's no actual calculations that they have to do. So they go down through basics, some background knowledge here. Depending on which version you're using for the West Point Bridge Designer, they give you like a cost analysis here for each of the parts. They're not always completely accurate because if it's a newer version, they've updated where this version is not necessarily up to date. That's not really a big deal. The kids will be able to figure that out later. And they do a nice job here stepping you through how to start the program. And then what I actually have them do, and I know for for some it's pretty anal, if you will. It might take some time, but I have them go through there and I have them fill out these charts. So I want them to see what the site cost is if it's a 24 meter down to a 0 meter bridge. And we're going to find out is the cost of the bridge, even though it's a shorter bridge, goes up for the site cost because they have to excavate down lower in order to build this. So they kind of play around with that. Figure out what it would cost if we do arch abutments, pier costs, cable costs, and there's all these different things that they point out where you have to select those, how you change those, where the total is going to be. It's pretty easy. So I do have them go through and fill out this stuff. All right, so let me open up the program. One of the things that I'm not sure if they still do this, because I forget, but when we used to install this program, it would come up with 3 links here. It would have West Point Bridge Designer for older computers, West Point Bridge Designer, which is like the current one for newer computers, and then the last link would be uninstall West Point Bridge Designer. And what would happen more times than I'd like to say is the kids would click that button not thinking and then be like, I don't have the program on my computer. So if they do have that link, you might want to get rid of that. So when you open this up, you can actually load saved bridges if the kids want to work on something for a day and they need to come back to it. Typically, the students are saving bridges if they get it to do something really cool, like when we go through the testing phase of it. The site cost is going to be listed down here at the beginning here for initial setup. So as we click through here, we're kind of setting up. You can actually compete. So there are different competitions that they hold where you can join a competition and there's different awards or prizes that students can win. I haven't done that. This is really where they're going to start to fill out those charts and change to see how when I change the deck elevation. Right now, my initial cost is $67,000. Well, if I go down a little bit, my cost went up. A little bit of an excavation cost. So they go down through and they change this to see what the cost is going to be. Then I have them go through and take a look at what the cost of the arches are going to be. So they can do different lengths depending on what they're going for here. And they can actually get into adding piers in. So if they want to create supports off of the pier, they can. But basically on those charts, they're going down through and changing, adjusting those and seeing how that affects their total cost. So I'll just create, let's see here, I'll create a 12-meter bridge. It's kind of halfway down. I'm going to say no pier and no cable languages. Okay. You can choose different strengths of concrete. You can choose different types of loading. Again, it'll affect your costs. What's nice for those students at the beginning here, if they're not really knowledgeable on like how to actually put a truss together, which they should be by this point, this should not be a problem for them because of the ad nauseum, the amount of truss work that we've done. But they can use some sort of template to help them out. But I usually tell them to use none. And then we can go ahead, finish, and start into this build zone. So you'll notice over here on the right-hand side, it's blank right now because there's no members yet. They give you these little circles here are your joints that you have to use. So they already give you those. And then what I'm going to do is just create a simple truss here. Drill in a couple of joints. And what's nice about it, you can see that it gives you a nice grid. And over here on the left-hand side or down here, you can see where it's snapping to. If you're not getting quite like here, you can see how it jumps a good bit. I can actually change that grid. I can make it a little bit smaller. Up here, you can adjust the grid size. So now instead of it being a large jump, I can actually get a little bit finer, a little bit closer. So I'm going to put those in place. Up here's my tool panel, so I can go ahead and choose the member. And what's nice about this is you used to have to click and drag to each one. Well, they got smart here, so I can click and drag across, and what it does is creates a member to each joint. And you can see over here on the list now, each of those members is listed here. So I'm going to fill in all my members. And it basically just gives each member a number based off of, in the order you created them. Sometimes easier if you have a mouse. All right. What's nice about this is here's all the members. I've got a basic truss that's working. On the upper left-hand side here, you can select this run the load test animation for the blue icon. And if I click it, it's going to go into my animation screen, and it's going to tell me if my bridge was successful or not. And what's nice about this is that if you have the red bridge, the red ones are showing you compression, the blue ones are showing you tension. If it's gray, it's showing you that it's under no force, no tension or compression force. The darker red, the more compression. The darker blue, the more tension. So it lets the student see where the bridge was experiencing the most amount of force. Depending on which version you have and which setting, you can go in and change the view settings. You can actually kind of pan around here. I don't know why you need to look away from the truss, but you can if you need to. You can go up and down. Gives the student a different perspective. You can actually tilt your head up and down too. Or if you want to get inside the truck, you can watch the truck. It's always fun when it crashes to watch the truck crash a little bit. So once you've tested this, what you can see in your chart on the right-hand side here is your compression and your tension strengths here. So for the students, they're trying to optimize their truss. Usually what I end up doing is giving them some sort of challenge to create, the cheapest bridge of a certain length without or with abutments or something to that effect. So how they do that is they have to figure out how to get these guys as close to one as possible without the truss breaking. And it's important that they do, whatever is symmetrical. So if they do something to this side, they do the same thing to the other side. So if you select one of the members, it's going to highlight it over here and let you know which member that is. And I could see that this one was under compression, and it's almost up at 1, pretty close to 1. So what I could do is I could take that member, and I can drop it down one size. So I just adjusted it from the 140 by 140 beam down to the 130, and then I can go ahead and test it again, see if it worked. And no, the guy didn't make it. So then I can find right here, now it shows you got these little lines in here. It says, okay, I've exceeded the 1, that threshold. I can't get to 1. 0.99 is the best I can get. So I can go ahead and I can increase that size again. And I can start to take a look at maybe other members here to adjust. And if you hold control, you can select multiple members, or you can actually highlight the entire bridge and adjust up or down as needed. So the students will play around with them. They'll try to get their cheapest cost. And they'll kind of play around with a couple of things. One is just the size of the member. That's pretty much the easiest thing they can play around with. The other thing would be, well, what happens if I take and I adjust the truss and I make it a little bit different? So I didn't adjust the size, but I adjust the length now. Is that going to change its strength? Is it going to be able to hold? I dropped the cost, so now I have less. So they go in there and they kind of tweak with their design. Part of the charts that they'll go through on this activity are found underneath here. Some of the information they need is found in the member details. So it gives them the size of the beam. It gives us what the cost is going to be per beam, what the material is, gives us our modulus elasticity, yield strength, all that type of stuff, that information that they're going to need for those charts. And the one thing we find out with the cost here is, if you had, say for example, we had an entire bridge here of 140 by 140 cross-sectional area beams, and then I decided just to take this one beam right here and change the size of it, what it might end up doing is increasing the cost of it. So even though it's a smaller beam, it might actually cost more because they factor in, if you had a build cost for this and I had all the same size beams but just one different, the manufacturer is going to charge you a little bit more because it's a one-off piece. It's a special piece. They have to manufacture just that one piece rather than manufacturing a whole bunch of them. So they have to play around with that to see how they can get their cost the cheapest. Up here, they can change the different materials. They can change if they want it to be a solid bar or a hollow tube. Hollow tubes are nice if you're looking at one direction of force. Tension, they're pretty good in. Compression, not quite as good in. So they'll go through, play around with this. I have a block, so we're about 86 minutes. And within a block, they can easily go through the activity and then kind of play around with it for a little bit. Any questions on this?
If the kids' truck just drives up to the edge and won't go across, it's because it's so dangerous that it won't go. So I tell them it's like, like a horse. It's like, no, I'm not doing it. So they have to be able to get a little ways before they'll crash. So if the truck just stops at the front edge, it means that they're not even going to get on there to give it a shot. You also want to make sure that your kids are all using the same version. If kids go home and use older versions, the product's cheaper. And so if you're having a contest of some sort that that compares, like the cheapest bridge gets the first point or whatever. If they have older West Point bridge, then you're going to be comparing apples and oranges. So just make sure that they're all using the same update. Because when I trained on one, and then I came and taught on the other. I was like, you guys can do better than that. And they're like, no, we can't. And so I built my same bridge in the one that I was having the kids use, and it was a totally different cost. So just be aware that there are lots of bridge builders out there. So if a kid's doing it at home or something, that you know that. I use this like Adam. It's my backup emergency sub-plans once we get to the point that kids have seen this. My kids all do it in the engineering class in the middle school. So it's not as much fun as watching kids do it for the first time, because my kids their goal is the biggest crash after not too much of an attention span. So kind of the thrill is gone because they've already kind of done the competition. But it is, kids who haven't seen it, it's not bad, and it certainly is a quality thing to do if you have to be gone and don't know you're going to be gone for me.
And Tricia, you had a question about what I'm doing with the mouse. I think put in the joints, if I'm correct.
Yeah.
I
Uh,
did.
okay, yeah, that was. I mean, I don't have a mouse, like a separate mouse. It's it's a laptop, so it has one of those touch pads. But once you select your joint, you just have to drag it around wherever you want and just left click, and then it'll plant one.
But it was my understanding you had to make the little white circles gray, and I had trouble doing that and getting it to add. And actually, when I tried to pull up the software, that was when I dumped out. So I'm not going to do it
Okay.
now. But I actually could not get I couldn't get the table to show up on the right-hand side.
Okay, that you have to toggle on if it's not already there. So the joints, like these white ones, they're already there. You don't want to put joints over top of them. It's just when you're going to add above, like your superstructure or your substructure. The member list, this thing over on the right hand side here, that's this icon on the top right hand side here. So if you just click that, you can open or close that. A lot of times when we're just building it, we just have it closed, and then once they start to really try to tweak and see who has the cheapest bridge that still works, that's when they really start to need this over here.
Well, I had watched the video, and I'd watched how they did it in the video, but they didn't explain what they were doing with the mouse while things were just happening. So I guess each time you click the mouse, it drops another joint, and then you click the mouse again, it drops another joint. And then how did you get the members to hook together?
Oh, okay. So
I couldn't figure it out. I fiddled around with it for, I don't know, a little bit of time. I couldn't figure it out.
So once you place your joints, and you can, like, typically what I do is I get all the joints out and I put the members out, and then you can always add joints or members later. But it's just a matter of clicking on the joint. You see how it highlights, and then dragging to the next joint, and then letting
So
go.
is your mouse held down while you're doing that, though?
Correct. Yep, I click and drag from one joint to the next.
So click and drag.
Mhm.
Okay.
That'll build that member then. And I can, you can add joints up top here. And what actually is kind of cool, when we do the 2-on-8, which is that truss build where the kids get in and actually have to design it, they do use MD Solids, but, that's a nice program too. A little bit more complicated. It's a little bit more free form than that. But they can see, like, a lot of students want to put in these joints up top here. And what ends up happening when we go and test this is it's like this whole top section is basically not being used. It's a waste. So it lets the students see before they go and build it, hey, this truss has more on it than what it needs to be. What happens if you get rid of this whole section here? They'll see the cost goes down, and they see that the strength didn't really change very much. So one of the other cool things about this is they let you save the iterations. So if you decide to try something, I'm going to do all this crazy stuff, you don't have to worry about losing what you just did. You can actually go back and say, oh, you know what, this was the version that I really liked, and it jumps you back in time, but it also still saves those other iterations that you can go forward again too. And it's kind of
And Adam, are those iterations from when you test it? Is it every time you test it, it saves an iteration?
Yeah. If you don't test it, it won't save your changes.
Right.
And then it also,
So,
up top here, it has a little icon that you can see that lets you know, well, right now it's under construction. I got to change this number right here. I'll make it, when it was 110, I got to bump it up a size or two here, and I can test it. And you can see right off the bat, before I even see it, that's not going to work. It's going to do that, you're an idiot sign. So going back to the activity, the students will go down through this. They're basically learning how to use every component of that program. Once they get down to the end, what I'll do is I give them a challenge, and they have to create the best truss that they possibly can based off of how to really utilize this program. And then I just have them paste one on the bottom here, or they can print it out and put it inside of we do like digital portfolios, so they add it to that. Any other questions on 2.4.1 or West Point Bridge Design?
So, Karen, you had mentioned that you have the sub do this. I guess I can't almost under any scenario see a sub doing this. So have you already, I guess, trained your kids to use the computer and they're at least familiar with it before you have
I've
the sub
got
do it?
I mean, even when I'm here, when I've taught this, I really don't lead kids through anything. I just have them read the activity and go through it. If you're willing to read the activity, it's pretty self-explanatory. Now that my kids see it in middle school, a lot of kids have already played with it. But even before it was part of the middle school curriculum, my kids could go through and really on their own. Probably their weakest point is they don't want to go through and do all the stuff. They just want to get in and click buttons and see what happens. You know, I like Adam, have them go through and fill out those charts because I want them to, I want them to show me that they went through and tried all that stuff. And so, no, my kids really, I mean, they're assigned a laptop. It's theirs to check. They use it in my classroom so they know which one they're getting and they grab it and they go. But no, I don't really do a lot of instruction on this. Now, if I have kids that just can't make this happen, and I do have kids that just can't get to a reasonable price, then maybe I would sit down with them and really go through getting rid of just the extra that they get, because that's what they really do. They have too much. When we talk about those numbers on the right and trying to get really close to 1 and, trying to have fewer parts and what happens with, hollow, when is that good tension or compression and that kind of stuff. But that's really the only time that I have to sit down with them. They kind of knock this out of the park, actually, even before they had seen it. So, yeah, I don't give them a lot of instruction. Em, do you just have them read and go?
For the most part, a lot of times I'm opening up and kind of show them what I really want to. What ends up happening typically is they just click past all of that stuff and just build a trust and play around with that. So sometimes I just have to slow them down and say, okay, no, first you have to get through how to use it, and then you can start building trusses. That's pretty much what I do. One thing I wish that we'd actually get into a little bit more, as in a calculation here, is the slenderness stuff. This whole column right here is actually pretty good. If they're trying to really make a really strong bridge but have the lowest cost, it's another column that they want to start looking at, because slenderness has to deal with the size of the beam, as in its cross-sectional area, in comparison to its length. So if you look at a beam that is 100 feet long, if it's only 2 inches in diameter, it's going to bend very easily just under its own weight. But if it's 10 feet long and it's 2 inches in diameter, it's going to feel like it's a lot stronger. So this ratio here ends up being a good factor, showing, okay, I can adjust this, I can get this a little bit tighter, and I can make it a lot stronger. All right.
Does anybody have any questions on chapter Unit 2 at all? And 2.1 was the statics. 2.2 is materials and manufacturing. 2.3 is the material testing. And I know some of you are just in 2.1, but anybody have anything they can think of before we start talking about Unit 3?
I did have a question. Karen, you had mentioned that you do the spaghetti bridge. What is the loads that you get on the spaghetti bridge? We're kind of right in the middle of that, and I'm trying to figure out how much sand to put in my bucket.
Well, my kids put a 2x4 over their bridge and then have strings that come up over the 2x4 that's hanging on the handle of the bucket. And then I have available about 100 pounds of sand. But we call them homers, the Home Depot bucket, one Home Depot bucket will hold a little more than 50 pounds of sand, to the level that I have a line drawn in it, just so if it drops, it doesn't spill everywhere. And so I have kids that make their bridges, and they get up to upwards around 50 pounds sometimes.
Okay, so I should try to use the Home Depot bucket.
Yeah, I would. That's what the competition we go to uses, and so that's really why I've modeled that. But they just said a 2x4, kind of perpendicular to the length of the bridge, and then we just pull ropes up over the handle, from the handle to over that board, and then I just have a old ice scoop that the kids use to load the sand into the bucket. And that's how they do it at the competition we go to. Some competitions actually use kind of like a stress analyzer, where they put a hook on the bridge and they have a piston that pulls down up to to the force that they're going to have. This is just the technique that the one we go to uses.
Okay.
But it can be pretty impressive. I had kids do prototypes last week, and the prototype is always stronger than the real bridge because they make them shorter, and so there's just not as much length. It's like what Adam was just talking about. And so we had to actually push on the bridge, on top of the board, to break the bridge so they could see where the cracking happened. So
do you give them a maximum weight?
Yeah, it has to be between 2 and 5 pounds.
Okay.
And it can't be taller than 6 inches. And it has to be between 4 and 6 inches wide. Okay. And it has to be between 32 and 36 inches long. Now, their prototype has to be between 12 and 20 inches, just so they get some practice on making it. But like I said, their prototypes are often stronger than their actual bridge because it's shorter.
Yeah, I think I gave them less weight to work with. I think it was related to the scales that I had. So I think mine is just about 750 grams is what I gave them. So I will probably have a lot less weight on that. And then you think the 2x4 needs to go the whole length of the bridge, or we're just a wood block?
Perpendicular to the length of the bridge. So, sorry, my lights were on saving mode here. So if this is the bridge, the 2x4 sits perpendicular to the length of the bridge.
Okay.
And so it's just centered, and if they have a superstructure, they have to have an opening for the 2x4.
Yeah, I gave that to them, that it had to be.
And then my kids win based on a weight ratio, I call it power ratio, so how much it holds compared to how much it weighs.
Yeah, I saw your rubric for that.
Yeah, and probably the best bridge I've ever had weighed in at exactly 2 pounds. Okay. And it held, I can't remember, I want to say almost 40 pounds. It was 30-something. And so, they were competing against bridges that weighed up to 5 pounds, but, they were going to have to double their weight to get that ratio in. So, yeah, it certainly adds food for thought, so you're just not making a big block of glue and pasta.
Okay. Thank you.
Mm-hmm. Anybody else? Chapter 2 questions? Okay. Well, let's talk about Chapter 3 then. And if you talk to people who go to training, one of the things people talk about is the marble sorter. And so I have a computer science background as well as math and physics, and so I personally love programming, but my kids and I love the marble sorter. So this is activity 311 that you see right here, and if you go into the modules, I'm almost afraid to ask this. Can everybody see that?
Yep.
Good, that's awesome. Good. I'm feeling so successful. Okay, so if we go down into Unit 3, so it's these control systems, and here's the Career Demand, Salary, and Education paper. I just assigned my kids this component of the paper. so that they're going to go out and look for colleges. My kids at this point have researched a field, and I swap the order of the paper. I have my kids research a field after we introduce the 17 fields of engineering, and then I have them interview somebody in the field they picked, so that they aren't all picking their neighbor in a field because just of convenience. So if they want to interview somebody that's not in their field, they have to rewrite the first part of the paper, which makes that less convenient. So I find kids really interviewing people who are in the field they really want, not just somebody that's conveniently located maybe in their own house or next door. So here's that at the ones, in 1, 1, 2, 1, 3, 1, 4, 1, you'll find all of the information on that paper. So that's in here. But in lesson 311, and I'm just going to show the VEX. If you have Fisher Technic is available. There are pieces of Fisher Tech that I miss, and that is kind of the Lego FUD factor of Fisher Technic. I think that the programming, the Fisher Tech programming, Robo Pro is what it's called, is a drag and drop icon-based language. It was a little more elementary, and the putting together of the parts was a little more elementary than the VEX and the Robot C. I'm a huge fan of the fact that we're actually having them use a language, and it's a C-based language. But 311, inputs and outputs in VEX. So in here there's a presentation that I'll talk about eventually. We'll talk about the parts. And the fact is, I have already at this point gone through part of this PowerPoint with my kids before we did the simple machines, because I wanted them to see the hardware part. But resources is where I want you to go now, and that's where we'll find this VEX test bed information. So this is what a test bed looks like from above. These wheels are in the air, as is this gear, as is this wheel. And it will talk about two versions of test beds. It'll talk about test bed A and test bed B. This piece right here is a flashlight, and if you have one kit to 4 students, then you have one flashlight and one photovoltaic cell, this little light sensor right here. You have one of those for every 4 students. I and almost everybody I know buys extras of those so that they do not have to create a test bed A and a test bed B, so that everyone has all the parts on their test bed. So we'll talk through here and see what they've got. But I put this on my website, and the kids follow these instructions to create this test bed. And it will take a couple of days in a traditional schedule or a full block to get this built. I hand out the big parts, so I ask, I say one person from each group come back, and I hand out, I have 12 groups right now in each class. I hand out 12 Cortexes. They pass it down the line. Everybody's got their shopping bag to put their Cortex in. I hand out each of these pieces, and they then take those, and then after they have the big pieces, they go back to their partner, and they can start putting them on. I do not spend a lot of time with this exact list. I do get like this, how many nuts do we need, how many of these screws do we need. I don't make the kids measure and make sure that they have 10 of the 3/4 inch screws or 16 of the 1/2 inch screws, that kind of a thing. If the screw doesn't reach, you need a longer one. If it's too long, you need a shorter one. But I do make sure they each have a bump switch, a limit switch, a line tracker, each of these pieces right here. The 2-inch drive shaft, that's the square long axles, is also what I call them. The gears we see here, so we talk kind of through all these, and we'll kind of talk about what these parts are today. Your battery, we'll look at that. LEDs, your flashlight, your motor controller, we'll talk about what that is. So I don't really do this shopping list where each of these little pieces, they're going to go worry about what size their screw is. So everybody has their base plate. I have them put a piece of tape on their base plate so that I know whose test bed is whose, because they all look alike if they made them correctly. I also have them put a piece of tape on the wire of their battery so that if you failed to plug your battery in to the charger, then you don't have a battery for the next day. Otherwise, first come, first serve, somebody who plugged their battery in for the next day might get a battery that wasn't charged.
Karen.
Yeah.
One of the things that I do here, which it just is functionality, kind of messes up a little bit with the where you plug the Cortex battery into the
this right here
is kind of annoying. So sometimes I rotate it 180 degrees. Yeah.
Right. This one right here, so the Cortex, and what Adam is saying is that the Cortex right here, if we go up, there is a battery that plugs into this side over here, and this bar is really in the way, especially for people with bigger hands. I can kind of get in there, but some of my kids who have really big hands have a hard time. So often my kids rotate this 180 degrees. If they make that choice, and I'll show you what I'm going to do with that, then they need to know that their wires are now going to the opposite side. So that's one thing to know. So here's that Cortex, and I want the kids to literally go 12 holes over, 5 holes up, and count. That's where I'm going to put the screw in, because I like them all to create the same base plate. I think following instructions is a nice skill set. But this is what Adam was talking about. If you face that base plate, or you face this piece right here is called the Cortex. If you face it the other way, the battery's a little more accessible, and the on-off buttons. So it is very specific. Like, Battleship, 23 over 2 up, that's where you're going to put your push button. Here we're going to put our limit switch, and it's going to be 23 over and 8 up. So everybody's test bed should look very, very similar, which is why I have them put tape on it. But you can see they're going to slowly acquire all of the sensors and put those on. Here are some parts. This is a little plastic piece. You guys have probably seen that. Those are spacers. There are small and large versions of those. This collar has a little inset screw right here. My set originally used to come with Allen wrenches that were T-handles, which allow you to put a freakishly large amount of mechanical advantage into anything you do. And I don't let the kids have those Allen wrenches unless they check one out for me because they need it to reach a certain spot in their build, just so that I don't have to Dremel out or Dremel off so many of these collars. Because notoriously I put a Dremel slot in here and have to unscrew that and trash the collar because the kids get them stuck and strip the inset screw. So I always have a conversation about there's tight and then there is it's not coming off. And so they want to put that inset screw in far enough that it stays, but not so tight that we can never ever get it off. You'll also, if you are inheriting a kit, you may find that these little inset screws are missing. You can purchase like a bag of 100 inset screws for it's under $5, and then you can just put those all back into the ones that are missing. So I just have the kids, if the inset screw's missing, we have a cup that they put it in, so I just know that I need to fill that in. So, it's very specific the way these little pieces are, and you have probably used some of these pieces in your building of your simple machines. This little black piece right here is the piece that changes that square hole to a round hole for your axle to go through, so you're not a square axle and a square hole. But it's going to be a step-by-step on putting this thing together. It's really just following instructions. Then here is where you're going to plug in all of your pieces. By changing the direction of your Cortex, one thing you do is you have the wiring's a little bit wonkier, but the wires are all long enough to reach, so it's not a problem. This is what the battery looks like. It's rechargeable every night. I have a charging station that I made out of a box that I just have the chargers sticking through. So kids just hook it up on that, and it's on a timer so that it charges like a Christmas tree timer, so that it charges for so long and then it turns off and then it charges for so long so that I don't get these too hot. Just an effort to keep a hold of those. But that's the test bed, and that is in the resource component of the module. So that's over here when you want to find that. We're going to look at this PowerPoint, which you can find under presentations or under resources. So it's the introduction to VEX Robotic Platform, the Robot C software, and my kids have already seen part of this because I show this when I'm introducing them to the hardware parts when we're doing the simple machines. But there's a picture of your test bed. So these parts your kids have all dealt with, right? I call this the disposable piece, the one by. This is the one and only piece my kids get to bend or alter. That doesn't mean that I don't find some of these bent and then unclaimed, like no one, like an elf belt bent them or something. But these are the disposable pieces. These one bys, I probably buy 3 or 4 packages of these every year because we cut them and bend them and they just don't straighten back out. Your kids know that some of these pieces have ends on them, which is certainly nice. You want to directly attach it and not use a gusset. But your kids have touched these parts because the simple machines are built out of these. There are the lock nuts, the wing nuts, and the regular nuts. I don't put these out for my kids. These are the ones that have that little white plastic nylon ring in them. If I was doing a competition, like I was doing a VEX competition, I would put these on because I'd be really interested in them staying for a very long time. But these are my favorite ones for kids to use. If it's a wobbly spot, maybe this one. But I'll have kids that really strip some stuff using these. So I just don't put those out. If somebody needs something to really hold, they can come get one from me. And the kids have all dealt with these screws at this point. I actually, for the first time this year, I'm teaching an all-girls class, and they were building their simple machines, and I was going around. I was like, these simple machines, you need to tighten the nuts on these. They're super wobbly. And I turned them over, and they were using collars to hold the screws on, which I guess was like engineering in some manner. But I literally had students that had never, ever put a nut on before. So don't assume too much. I'd probably say righty-tighty, lefty-loosey. I should make a T-shirt that says it because I say it so many times in class. But but your kids have had experience by now with those. The gears, I have a poster that has each of these gears on it and has the number of teeth so that the kids aren't sitting around constantly counting the teeth. So, you know, some of them have this shape with the holes, some of them are the bigger ones with the swirls, and some little ones. And these are the fine tooth gears. There's also wide tooth gears. But I have just a little poster that's got a picture of each one and says what the tooth count in it is. It just saves us some time. Then we've got 3 different versions of wheels. I had to purchase more of this brand of wheel. It looks like a rollerblade wheel in my opinion, kind of like that, for my solar cars because I didn't have enough of those in the kits. But we have gears, wheels, motors, and servos, and we'll talk through those. You probably have 2 kinds of motors. The smaller motor is the 2-wire 269, and the more powerful motor is the 393. It's bigger. I limit my kids to everything on their test bed they may build with, and then depending how many classes I have and how many leftovers I have, I divvy up parts so that everybody has eligibility to the same number of parts. And so if you need a part that you don't have, you may have to swap with another group, but you can't get another one from me. And a motor is something that they end up having 2 of when they go to build their big build. So I give them a 269 and a 393. Both of these are 2-wire motors, and the controller where you, the Cortex that you plug in to get power from needs a 3-wire plug. And so this little controller right here, this motor controller, converts it from a 2-wire to a 3-wire. I have one of these on each of my motors. So when you pick up this motor, it already has a controller on it. When you pick up this motor, it already has a controller on it. The other thing that my motors all have is they have motor screws already screwed into these spots. If you were going through your screws, you may have found out that some of your screws have a smaller diameter than other screws. And the motor screws have a smaller diameter. The new kits, the motor screws are all gold, which is nice. The old kits, they were also black. But I go ahead and put a motor screw in each of these. So every time you grab a motor from me, it's already got the controller on it to convert from 2 to 3 wires, and it already has the motor screws in it. When you turn it back into me, you need to make sure those motor screws are back in and the controller is attached. If you have a kid who turns on whatever they're building and the motors just start running incessantly and they're not reacting to the code, there's a very good chance they plugged that 2-wire prong into the Cortex and didn't put the controller on it. There is a motor that looks very similar to the 269 and the 393, except that its cord has 3 wires, a white, kind of an orange, and a black, and these have just a red and a black until we put the controller on, which converts it from the red and the black to the white, orange, and black. But this is a hot commodity, the old servo. The servo motor is a rotationary motor, but it doesn't turn 360. It only turns 120 degrees. But the distinction between it and a regular motor is that you can program it to stop and start at specific degree placements. So if I wanted to turn to a 30-degree spot, I can program that. Versus my motors are controlled by time and speed, which in a very precise piece of equipment should consistently give you the same distance, but nobody's doing surgery with VEX parts, and so the regular motors are not as precise at starting and stopping. So I always tell my kids to not control distance with time. There's actually one of the investigations that they do, they show the kids that if they use time to control a distance, it actually isn't very accurate. So that's one of the things that they'll do. But this is a servo. Again, you can tell it's different than the other ones because it's got these 3 wires coming out of it. It does not need the controller wire for that reason. These are the sensors. They have not played with these because these are the smart parts of the Cortex. So this is a bump switch. This is a limit switch. This is an on-off, just like a light switch. Same thing here. This is an optical shaft encoder. So that encoder actually has 2 wires on it. It uses 2 of the plugs. And it's a counter. It counts how many times it rotates. So you can use it to, as opposed to that servo, you can use it to count how many times a wheel turns and stops it. I have some kids who are competing in Science Olympiad right now, and the challenge this year includes a motorized vehicle that meets like 3 different requirements, and one of them is it has to stop as close as possible to a certain designated distance, and they're using a shaft encoder for that. This little thing that looks a lot like a speaker also has 2 wires coming out of it. This is your rangefinder. This is your light sensor. This always goes in pair with a battery. Like in my room, my ambient light, I have one side of my room that's got a huge window, and depending whether it's nighttime or daytime or cloudy or not, this light sensor will read differently, so I always have the kids put a flashlight on it if they really want to use it. This is a potentiometer. This also manages some turning motion, but it's got some little warnings with it, some caveats we'll talk about. This is a line follower. It reads white and black. We'll talk about it. If you have ever seen any VEX stuff where when you got your VEX stuff, you had these mazes that you folded out, these huge floor maps that are mazes that are white and black. That's so that you could make a vehicle that stayed within the lines, followed those lines based upon that line follower. So this is the potentiometer. This is the one that I said has some caveats to it. It is an analog sensor, which means that it will produce a range of numbers versus being a digital sensor that's either yes or no, on or off. It measures a rotation between 0 and 265 degrees, which you notice is not a full turn. That 0 to 265 is converted to a number between 0 and 4,095. And I forget the computer base that uses that conversion. But this is a big, big caution. If there is anything that children have purchased from me, it is a potentiometer. The internal mechanical stop prevents the potentiometer from turning a full revolution, because we said it only goes 265 degrees, but it doesn't take hardly anything to turn it past that. So my rule is you are not allowed to put a potentiometer on an axle with a motor without my approval, because it's really easy to have a motor accidentally start running and you not mean it, and it just takes it past. And it takes almost no pressure to snap this. And all you have to do is, if you can turn this more than 265 degrees, it's now broken. There's nothing you can do about it except buy a new one. An optical shaft encoder. It is a counting tool, and it has 360 counts per revolution. So essentially every degree is one count, and it can count forward. So if I rolled the wheel one circumference forward, it would count 365. If I wanted to roll it back, it would negate that, and I'd be back at 0. So it does allow me to move back and forth. So it can control what the distance the car is, or your vehicle, whatever you're turning, is traveling. There are much smaller versions of this now. There are actually motors you can buy that have encoders attached to them. This is the ultrasonic. And I tell any kid that's got a motion sensor in their house, or like on their front porch, that when you walk up to your porch, the light turns on, you have a motion sensor. If you have an alarm system with a motion sensor on it, so it's going to send out a signal, bounces back, and it's going to return distance. And you can set that in either inches or centimeters. Now, it works in a conical form, so the farther you are away from that sensor, the wider it reads. So if you've got stuff over here, it's going to pick it up if you're very far away. Depending what it's bouncing off of, I know one year in the VEX challenge, they had to drive a car up to and stop as close as they could to an object, and one of the objects was a stuffed animal, and it bounced back the distance different than like a board did. So they need to know what they're bouncing up against to get a good reading. Adam, should we stop with this part of the sensors, and we can pick up on this when we come back together?
Yeah, sounds like a good point, because this is basically going over the parts and pieces. If we start in on the program, a little bit more.
Yeah. So to the question that I see here about when you're unpacking how many test beds, you can get 2 test beds from every box, but you'll have an A version and a B version, because you won't have enough flashlights and light sensors. Do you remember what the other thing is that you don't have enough of?
Servo and the...
Right.
Is it the sonar?
Yeah, maybe. So that's why they make a test bed A and a test bed B. And test bed, one of them has the servo, and I think it is the sonar, and the other one has the flashlight and the light sensor. So if you have the funds to add however many sets of those, then it's a nice idea, and then you can have test bed A and test bed B, and everybody's got one.
Yeah, I think it was about $50 per kit.
Right. Right. It was well worth it. A great purchase. Whoever you have to beg, borrow, or steal from, it certainly makes it a different situation than waiting for the kids to have to catch up to where their other guy is.
I know that to answer your question, Griselda, that you have 4 classes, but only 8 boxes. Some of the people that I know have taught this that don't quite have enough VEX actually switch Unit 3 and Unit 2. So they'll teach Unit 2 to 2 classes, Unit 3 to the other 2 classes, and then flip-flop them when they get to that point. It does definitely make it a little bit more of a headache, but you know, if you have to, what you got to do.
Yeah, that'd be you are not going to get, well, I don't know how big your classes are, but in theory, you can get 4 students per kit. I had a peer who had their kids build it and take it apart every class period, and I cannot even wrap my head around that. I think my kids would just not come back.
I would not.
Yeah, I can't. I think that's just not a good choice. 25 students per class. So you have a curse. You have an odd number. But I would say that's probably 12 groups. So you're going to get.
Yeah, I mean, if you had to push it, you could do, 3 kids per group, 6 kids per kit, but that does push it.
Mm-hmm.
I mean, you could.
Yeah, it does. You definitely aren't going to get more than 2. You are not going to pull off more than 2 classes with that many kids. So I would like what Adam's saying is that everybody I know who has to do it does 1-2 with one group and 1-3 with the other group, and then swaps them. Fisher Tech, Adam, there is, Tricia, when you go into 3-1, there's a VEX option or a Fisher option.
Yeah.
So when you go into the modules and you look at 3-1, there's a VEX module and a Fisher module to see there.
Yeah, the VEX, your files will all be like FE, whatever it's called, and then the VEX files will all be VEX, whatever it's called.
Yeah, and I think it's all in one group.
Yeah, now supposedly that's not really supposed to be here anymore, because they were we switched from Fisher to VEX. They're not really supporting the Fisher files anymore, but I guess they're just going to keep them there. So if you are going to be a Fisher person, you may want to just make sure you save these files, just in case they decide to not post them some point later.
Yeah, and they've actually held on to them a lot longer than I thought they would.
Yeah. You go on the left-hand side, I went under Files and then just to Unit 3-1, and it had everything there too.
Yeah, if you go, you guys can still see my screen.
Yep.
Here's where I was. I was in Machine Control VEX, and you just want, if you have Fisher, you want to be in Machine Control Fisher Technic. But I agree with Adam. I'm not convinced this is going to be around forever. So I would drag those and save them if you want them. Question on the same compound machines.
Yeah.
I let whoever built the pulleys gets to use pulleys, and if you didn't build one of the simple machines with pulleys, you don't get to use pulleys. That way, I at least have 2 versions of the machines. I do a pen clicker, so all my kids make a pen clicker on the compound machine. I have friends that give them like 3 options, so 3 different things that they can do. But no, my kids all are supposed to bring me their designs. Now, do they all end up with a lever and a wheel and axle? Yeah, they do. I've seen like 4 versions of it. By making some kids have pulleys and some kids not, I get a little variation.
Yeah, I like to have them, whatever they build in 1-1-1, I kind of have them keep it put together, and then it encourages them to use that when they do 1-1-6. But I do the same thing. I give them some sort of challenge in the end, like pouring a cup of water, or turning a light switch on, or hitting a space bar. on the keyboard, but some sort of challenge in the end.
Tricia, if you got Fisher Tech, I totally get that. My school bought Fisher Tech, and then the next year, Project Blueberry changed to Vex. So it was a pretty fun board meeting when I got to stand up and be like, "Hi, remember me? Because I just asked for $30,000 last year. I'm back, and I need $30,000 again." It didn't go over really well. So I get where you are with that, and I think so does Project Lead the Way. But I agree. Get those files downloaded in case you're going to be the guy using Fisher. Though I do think you can probably get Fisher pretty cheap. I bet online somewhere they're probably pretty easy to find.
I've got boxes of the stuff just sitting around.
Yeah, I shipped it down to our middle school and wrote some stuff for them, but yeah, I get it. Okay. Okay, anybody else? Okay.
All right, we'll meet again then on the 16th, I believe.
No.
No?
Yes.
Yes?
Yes. Yeah, 16th.
And then we'll get into Robot C and start to talk about the basics of programming that night.
Right.
So I guess that is a question that I have. So I try not to plan my lessons like a day at a time. I actually try to get the whole unit, kind of understand where the unit is going, kind of pull the whole thing up together, put my brain around it. I spend 4 or 5 or I don't know how many hours kind of looking through the PowerPoints, looking through the exercises, wandering around my room, making sure I have all the little parts. And I try to do that so that once I start a unit, I kind of have an idea where it's going and I can present it as something that's a little bit cohesive. So one of the things that's been a little bit frustrating here is I'll do that and I'll download it all and then we'll kind of get to, oh, I don't do this because that's kind of silly and, oh, they don't like it that much. And so I'm kind of looking for, where is this going? I mean, are we, I just, where is the whole thing going? And what am I going to need to know? So I've taken programming. I'm actually learning to code in Java because I'm the AP Computer Science teacher too, but I've never put together a robot in my life, and so I'm kind of not sure where to start. I think I could probably line up what some of the pieces are just because we've worked with Fisher Tech so many times, and I'm like, that looks like a light, or that looks like a little solar panel. So
well, that PowerPoint I started to go through tonight, there's an equivalent to that in Fisher.
Okay.
So if you look in your Unit 311, it will have that equivalent. And it does the same thing in 311 where it goes through and it will run you through, I think in Fisher also, it's 7 different little activities in which they mess with every single different sensor.
Okay.
And so they write little programs about, getting it to move a motor, getting the light to turn on. In Fisher, getting the electromagnet to turn on and off. So you'll go through each of those little activities, and if they pay attention and actually do those activities, they'll be trained in both coding and the parts by the time they're through all of those. And then the goal,
go ahead.
The goal is to create that ultimate machine that they have to figure out how to build it and how to program it.
Okay.
And it's much easier in Fisher than it is in Vex, actually.
Okay, and then my question is, so like with the structures, we got to a couple of them and it was like, well, this was not so good, we didn't do it, and well, we only do this one when the sub comes, and that, so well, we do everything in 3-1.
You've got my website, right? And you have last year's calendar. If you've seen my calendar?
Well, actually, I saw this year's. I guess I didn't go to last year's calendar because this year's it's kind of like revealed as it happens. So if I'm a day behind you, then I can only see what you're doing tomorrow as opposed to.
If you go back to last year's date, so instead of 2016, put 2015, you will see last year's calendar.
Okay.
And that is my entire year mapped out, and you can see which ones I do and which ones I don't do. And to be honest, there are things that Adam does that I don't do, There are things that I do that Adam doesn't do, and that really comes down to what equipment we've got, what else we're doing to cover that curriculum, you know, and who our kids are, what experiences they have. And so, but I will say, the first year I did this, I did all of them.
Yeah. Well, I will also tell you, I completely applaud that approach. Just some things work better for others, but right now I don't know what works. I don't know what doesn't work, and I'm not even sure I have all of the equipment, or that all of the equipment I have works. So I'm trying to stay ahead so that you don't end up having the one day where you turn everything on and then nothing works. But that's like today's lesson. So.
Yeah, I have that annually, just so we're clear. I plan for 2 days for my Robot C and my Vex Cortexes to not talk. And I let my tech people in district know today's the day I'm doing this. If you could come support me, that'd be great. But I annually waste a day or two trying to get my Robot C and my Vex to work. Now, I never had that much difficulty with RoboPro and Fisher Tech, so I think that's a little bit easier connection there. But yeah, go to my calendar and you can just go back to last year's dates, and you can, when it says up in the corner where it says what is the date, or just go back a month at a time, and you can see what I choose to do and how I pace it. But you know, Adam and I have done several things where I'm like, no, I don't do that, and I do this, and he does vice versa for that. So, you know, just depending how we go about it. You can also, all my reviews from last year are online, and within that review, you can see what content I deem to be important. My kids are really successful on the end of course exam, so I'm pretty happy with what I'm choosing to teach them, and you can see by the reviews what it is that I prioritize.
And I'm not, I don't object to looking through. I'll have to tell you, between what's in the LMS and what's on your whole website, there's so much information. I'm just trying to like cut the path forward that, you know, instead of looking at everything and deciding what I need, I'm really trying to kind of get the best recommendation for the first year through. Yeah. Because really time is my limiting factor. I mean, yeah. I would love to sit around all weekend and do it, because I'm already sitting around all weekend doing something else related to school most of the time. So it's really, I'm just trying to be efficient, that's all.
Well, that's what some of I mean, I don't know if we're where you are or if we're not far enough ahead, but some of the times we're trying to save you some time and not do certain activities.
And I appreciate that. I'm just trying to, as I haven't, it's on my list to kind of put my brain around Unit 3, and I probably have about another maybe 10 days or so in the Unit 2. And anyway, I'm just trying to, like I said, be far enough ahead, but not too far ahead. And I don't know how to do any of this. No, but I'm going to learn.
I get where you're coming from. I mean, to help you out a little bit, in Unit 3.1, the Lesson 3.1, you know, I do all of that. All those activities, they really build. It's like a lot of the other units don't build quite the same way, but this one really does. So it does a nice job.
Yeah, because I liked one, because one kind of, all those little pieces built on them, and, you know, the poor lady who said 1.1.1 went lousy, but my simple machine it wasn't complete disaster, but it wasn't very impressive at all. Yeah. But by the time they got to the winch, and then the winch went to the car, I mean, they were really darn pleased with where they were, and I was actually pretty happy with where they were too. Yeah. So I actually like the ones that build, because they can see it, I can see it, we can all see it, whereas the structures was kind of, anyway, it was just a little bit, I kept looking for that, but it wasn't there. But that's, I think, just the nature of those different topics that were all put together. So. And called structures. So anyway, that's just the way it is. Well, thank you for that advice on that. And I had not thought to look at last year's calendar to see what's coming up on this year's calendar, but I can go back and do that.
Great. Thank you. Let me know if it's weird and you need my help talking through it.
All right. Thank you.
Yep. Good luck.
All right. Bye-bye.
Robin, are you still out there?
Yeah,
Okay,
can you hear me?
Yeah, I can. I told Adam, I
Good.
asked him, I was like, have you read those supplies? And we both admittedly just do the thing we've always done.
Right.
But yeah, I have an 8-foot long piece that I sit on top of 2 footers. And actually, I don't use cinder blocks. I use, they're called deck footers.
Mm-hmm.
And they're like kind of look like a little pyramid, and they have a T-shaped cut, like a plus sign cutout. So you can either put the boards in joist position, or there's a little cutout for plank position, which I think is way more secure than the cinder block.
Where did you get that?
Just
Can
Home
you
Depot.
post a picture of that? Can you
Yeah, I
post a
can find
picture
it.
of that? And then
Yeah.
I actually had a question about the 2x4. So we did the 2x4 one, and we were off by like 35 pounds on the kids' weight. And I didn't know if they jump on the, so I used the 2x4 in my classroom. I don't know how old it was or how long it had been there, but is it possible to like break the modulus of elasticity? Can they like jump up and down on it enough to like make it
Well,
not
the fact
good?
is you calculate that every year, because the beginning of that process, you calculate what the modulasticity is of the board, and then you use what you calculated in the next one. So, so it should be what it is at the time. Ironically, this year I actually, one of the kids broke the board, which was like thank you, Adam's got it right there.
There you go.
Was a pretty amazing feat, but no, and the key comes down to how precisely they measure. So you want to make sure, you'll notice in the instructions it says to have a ruler that can measure to a 32nd of an inch. And that's really the long and short of it, is if you have an imprecise measurement, you're going to be off on weight. I think we're usually 10 pounds is a lot off. We're usually within 5 or so.
But what I also found is that you had a kid kind of wiggling and bouncing on the board. I didn't have this thing that made it more stable. And then you had another kid with his hands between that kid's legs, like trying to measure it. And it was just awkward.
Yeah,
it was a very quick and dirty sort of a thing, and nobody wanted to be hanging around in that position for very long. And so I think what we concluded it was about.
Yeah, I assigned several roles. I have a kid on each block end, just to make sure the board doesn't flip. I have a kid who is volunteer 1, who is on the board, and volunteer 2 is their support person. So they stand so that that person on the board can put their hands up on their shoulders until it's time for them to weigh. And then I have 2 kids that are on the other side of the board who are the measurers. And so I have about 6 people involved in the process. And we, get to the point where they're not jiggling up and down because they're using the shoulders of the person in front of them. And it really comes down to how precise the reader is. But if you have, if you have 2 people reading, it's a little, I think, less awkward. You have somebody who they're shouldering on, it's a little less awkward. And then my readers are always at the heels of the person instead of at the toes of the person, because I think it's a little more.
All right. Well, because that's what we finally concluded, that when they said, oh, it's about 3 point whatever inches, that it was the about word that kind of got us off by 30 pounds. Because when you're measuring such a small distance, it can, it just makes a huge error. So.
Right. So 30-second split inch is a good thing.
Yeah. Okay.
How much are those? Do you have any idea?
Adam, do you see prices? They're under $10.
Yeah, they're cheap.
Okay.
But the real question is, how much do they weigh? Because you have to carry them up to your classroom.
Yeah, no more than a cinder block weighs.
No way.
But I think they're under $10.
Okay, good. All right, great.
But they're a lot more secure for me than a cinder block
Yeah.
is.
Go around to a job site, you'll find a couple.
Somebody's backyard.
I'll drive around. I brought a cinder block from home that my husband gave me, but I have a feeling we don't have any of those, so I can afford to stop and buy those.
Well,
I think I got both of them for under 20.
Oh,
I got both of them for under 20. So.
Okay, good. All right. Well, I appreciate the help.
No, well, thank you very much. Good luck with that one.
Yes. I'm looking forward to it.
Robin, I will send you my website link, okay?
Okay. That sounds wonderful. I'd like to have that.
Calendar and see the stuff I do.
Yeah, I need all the help I can get.
No problem.
Okay, thank you.
Good luck.
Thank you.
Bye-bye.
Bye.
All right.